Okay. This week, I am very excited to speak with Dr. Travis Sawyer. We are going to discuss not only how he got into optics, but his dissertation, Multimodal Optical Imaging for Tissue Characterization and Disease Diagnosis. It rolls off the tongue. And then in general, we're going to discuss your lab, which is really kind of a continuation of your work, is my understanding.
Thanks so much for having me, Logan.
Yeah, absolutely. So just to kind of kick things off, before we dive into the dissertation, how'd you get into optics, much less biomedical optics?
Yeah, great question. I think that everyone has a different path in how they get here. I'd say that I was exposed to it at a pretty young age because my dad was in the astronomy field, and so I was always kind of aware of optics peripherally. I was interested in astronomy, and I started off as an astronomy major in college. I ended up switching to pure optics and optical engineering after I had some health issues, and in that process, I got exposed to a lot of medical imaging devices, medical imaging equipment, and I got kind of fascinated in that concept of image formation and how we can visualize different functions or processes using different technologies. And so that was at the beginning of my college career, and so I switched into optics. I didn't actually start pursuing biomedical optics until kind of the end of that, when I was a senior undergraduate and then into graduate school. But
And sorry to interrupt you, where was your undergraduate?
So I did my undergraduate here at the University of Arizona. Okay. So I've basically been here the whole time. I took a brief break to go to a master's at University of Cambridge in England, but undergrad, PhD here at the U of A. So.
Okay. Yeah, I always like, for myself, I have the dumbest reason for getting into optics, much less biomedical. When I did biomed, which was that I read sci-fi, and you read some of this stuff and you're like, this feels crazy, and then you learn about biomedical stuff, and this is it, right? There's the bridge. You're doing pretty wild stuff for prosthetics or retinal things in the world of optics, etc. Much less imaging devices. I think yours is probably a better, maybe a cleaner motivation to go into it. But I still sympathize with a lot of imaging optics, especially in the medical realm, feels very sci-fi, especially when you're younger, of like, you can see inside me, right? You can, not only x-rays kind of make sense, but you can kind of see with MRI and OCT, which we'll discuss. So anyways, that's kind of a nerdy digression, but...
No, I'm a big sci-fi fan too.
Okay, perfect, yeah. So your dissertation specifically kind of covers this discussion of multimodal optical imaging and for tissue characterization, disease diagnosis. And specifically, you looked at endothelial cancers of ovarian and esophagus
yes.
in the ovarian and esophagus domain. So why just that, I guess? I mean, why not other cancers?
Yeah, I mean, that's a great question. Honestly, a lot of people are looking at other cancers. I think that it's kind of a big problem, big disease. It's one of the leading causes of death, as probably a lot of us have experienced personally as well. And so in terms of a dissertation, you of course need to scope it to some reasonable amount of work. I think that
Don't tell your advisor that. Although you're on the other side of the table, so it's an interesting question. But yeah.
Yeah, no, that's funny. Yeah, so I think one good thing to consider though is which ones are most easily accessible with optics. And so things like bone cancer, you couldn't really do much with optics since you're not really able to image inside of the bone using visible wavelengths. But esophagus is a great organ for that. We already use endoscopes for screening. One of the kind of facets of my dissertation was focused on microendoscopes, which leads into that ovarian cancer realm, since that is much harder to reach. But my advisor, who still is pursuing the work, Jennifer Barton, she's pioneering there and collect the kind of data that I worked with in my dissertation.
And we will certainly get into kind of the modalities of how these optical systems are put together, but I feel like for the audience, them being small and the motivation for that should be pretty obvious, right? If esophageal, it's kind of going down your throat, they're imaging something in your esophagus, ovarian, other modality, but anything that's going to go inside your body, you want as small as possible. It's going to be uncomfortable. You want it to be as minimally uncomfortable as possible, right?
That's exactly right. I think especially for endoscopes, where you're essentially trying to insert it into an existing aperture, you could say.
Right.
You don't want to really break any tissue, and so keeping it at that diameter or smaller is kind of the name of the game.
Mm-hmm. Okay. So let's kind of get into the motivation. I feel like it's pretty obvious. Cancer's bad. Everybody knows this. But what kind of numbers are we talking about? You give kind of the 5-year statistics for existing, so using the current methods in clinics. That's an important distinction for survival rates for ovarian and esophageal cancers. So can you give those?
Yeah, so that, off the top of my head, I think that the one that I always remember is this will lead into the motivation, is the 5-year survival rate when it's detected at a later stage. Mm-hmm. And that tends to be below 30%, maybe 25 or something like that, both for ovarian and esophageal. And then if you look at what is the 5-year survival rate when it's detected in the early stage, it increases dramatically, something like 70 to 90%. Mm-hmm. And so you get a factor of 4 or 5 improvement by detecting it early. And so that kind of leads into the whole premise of this idea of advanced optical imaging, is that not only do you want to know that the cancer is there, because honestly, sometimes you have a giant tumor in your throat, you already know it's there. Yeah. But you want to find it in those early stages because it is so much easier to treat and manage and lead to those better outcomes.
So there's a lot of questions I guess I have about this, and I might get them in the wrong order, but let's just start off with why is it better? Like, I guess what's the approach if you find out that I have a large tumor in my esophagus versus if you find out, well, you have a small lesion that's forming, right? So early versus late detection. Sure. What is a doctor going to do?
Yeah, no, excellent question. So I think one of the main factors is metastasis. And so that is the process by which cancer, after it's developed in one organ, it then spreads to other organs. If a patient experiences metastasis, it will be very difficult for them to be successfully treated and live a long life. And so by catching it early, you essentially are catching it prior to that metastatic phase. Mm-hmm. I'd say that's probably the most important. Other factors to consider that, bigger tumor means you have to remove more tissue. It starts to obstruct other functions that might be occurring. And so while that might not directly lead to survival or not, we'd call that morbidity. In that, let's say you have a giant stomach tumor, you might have to have part or your whole stomach removed, and living with that is not pleasant. And so, smaller amount of tissue removed, easier to come back from, and you really prevent that cancer getting to the point where it metastasizes.
And if I'm familiar with it, I was very fortunate to get to shadow a doctor when I was, I think it was when I was an undergrad. And so I got to see some treatment for Barrett's esophagus and for, lesions detected in the esophagus. It's really good if you can detect it early. I fully agree with you. My takeaway was, oh my God, this is really brutal. How they remove it. They ablate the skin and I don't know if our audience wants to get into it, but it's basically you're going to remove that tissue through a not fun process. But that's better than you have a big tumor and we have to really kind of excise a lot of tissue. So
yeah, definitely. So, and to be honest, the treatment methods have been a bit brutal in the past. Obviously, removing massive amounts of tissue or burning it with a high-powered laser. I don't think anyone wants to go through that, but those are advancing as well. And that a lot of the work in pharmaceutical research and it's called immunotherapy, but they're essentially developing specific drugs targeted to a patient's immune system. There are a lot more sophisticated ways to go about treating cancer now, but many of those are only just developing. So I can imagine in the future, even in the case of having a tumor, the approaches might not be as invasive or as painful for the patient.
Right. But nonetheless, you want to catch it early. Even if it's unpleasant, if you're going to live, that's better.
Yep. Same reason we get colonoscopies at, 45 now? That essentially colon cancer, it always, tends to pop up after the 40s. We are having more issues these days with early onset colon cancer and whatnot, so they're actually pushing that date forward. But basically, they did a cost-benefit analysis and found that if they gave everybody, free colonoscopies starting at age 45, they would save more money by not having to treat them for cancer later on.
Yeah. And so I think that bridges really well into my next question. Maybe a lot of the people listening might be thinking, well, yeah, I've heard of colonoscopies, or you can give yourself self-checks for various other types of cancers, or skin cancer, a doctor might take a look. So people probably aren't as familiar with esophageal cancers or ovarian cancers in terms of how you check for them. Or maybe they are, and I'm the odd man out. That's totally viable. But how do you check for them today? Like why do we don't do a good job of detecting them early? So why is that?
So one of the reasons is that they don't produce noticeable symptoms in the early stages. And so it's very difficult to check for early esophageal or early ovarian. Mm-hmm. In fact, for ovarian cancer, there's essentially no way in which you can do an early or like some kind of screening test. Esophageal, they do have endoscopies, and they'll do that for high-risk patients, those that have what's called Barrett's esophagus. Gives them maybe I don't remember the exact number, but it's something like 10 to 30 times increased risk, which sounds like a lot, but 30 times a really small number is still a pretty small number.
Yeah.
And so that's essentially the protocol for esophageal. Ovarian, they really don't have anything. They can do like pelvic examinations, but the symptoms there are so non-specific that they might just be having cramps that are normal part of their cycle, or it could be an ovarian tumor. Mm-hmm. And so in that case, that really motivates the need for new ways to do these checks, specifically for patients who are at high risk, because for a healthy patient who doesn't have any genetic predisposition or maybe not any major risk factors, the chances of developing these are still extremely low. And so it's not something that everybody should go around worried about every day.
Right.
But just be aware that if you're having weird pains, that you might want to go talk to a doctor.
Right. So you kind of put it pretty clearly in the paper, but and you just reiterated that the diagnostic methods are either non-existent or just not ideal. Mm-hmm. Let's call it that. I think that currently, I want to say that certainly for ovarian, but I think that you included esophageal, there's no recommended regular diagnostic method. Mm-hmm. So there's a clear motivation here. You chose, maybe, I shouldn't put this on you, but you chose to utilize optical methods. But there's a reason for that, right? So what is it about cancer cells, and particularly these epithelial cancer cells, that stands out to make them good candidates for optical methods? Besides the fact that, if I'm sticking something inside my body, I want it small, we can do that with fiber optics, but why else would you use optics?
Yeah, sure. No, I think this gets into really why I'm so fascinated by this field. And I could answer that in a couple of different ways. First, I think is an obvious one, which is resolution. That if you're looking for really small lesions, could be on the order of a couple millimeters. If you use a larger scale imaging modality like MRI or ultrasound, you might not have enough resolution to actually resolve the lesion you're looking for. And so,
and I apologize. I'm gonna interrupt you. Can you just define lesion for our audience?
Yeah,
I probably haven't heard that term, but
no, sure. I usually think of a lesion as just like an odd mass or something that you don't know if it's cancer. It could be something completely different, but a suspicious area that you want to check out. And so that's one reason is resolution is important. I think for early stage cancers, it's small because it starts off as one or a few cells, and you don't necessarily catch it at the phase where it's a single cell, but still you want it before it gets a huge mass. Then I think the second, which I find more interesting, is what I would refer to as the contrast mechanism. And so contrast in an image is anything that makes it bright or has a difference from the background. Mm-hmm. So that if the background is bright, then it's dark. This occurs in any type of imaging. So X-ray, what produces the contrast is absorption. For optical wavelengths, you can have different types of contrast mechanisms. We might talk about OCT shortly. That's all about microstructure. And so anytime you have different refractive indices, you'll have some back reflection of the light, which lets you form a nice 3D depth profile using OCT. Cancer really disrupts the microstructure. You might have nice ordered tissue, and then you have a giant tumor growing, and that's going to totally mess everything up. Mm-hmm. So it appears really nicely on OCT. Other contrast that we look at is fluorescence. And so that can either be some contrast agent where you inject it. I'm more interested in natural tissue fluorescence. And so things like the metabolic process of cells produces these cofactors that naturally fluoresce in different wavelengths. And so by using spectral imaging or some kind of spectrally resolved detection method like spectroscopy, you can get a measure of how the metabolic activity is changing, which again, when you have cancerous tissue, it's usually quite active because it's trying to replicate itself. Another big one is blood. We can capture some nice blood spectra. Specifically, it absorbs light in a really well-defined pattern. And that also varies whether it has oxygen or not. And so both blood abundance and oxygenation tend to be one of the kind of main markers of cancer. And so we can use that to visualize the microenvironment quite well. So contrast and resolution, I think, are kind of the two main things I like to think about when we're talking about biomedical imaging for like cancer screening and detection.
And so you reference it. I don't remember the exact organization, but I think there's 8 commonly accepted kind of unique but common characteristics to cancerous cells or cancer that's kind of going nuts in a negative term. And you just laid them out. My interpretation, please correct me, is there's going to be small microstructural changes. There's going to be big structural changes. And then there's going to be chemical changes. And so we'll delve into why OCT, multiphoton imaging, and fluorescence are what you chose. But I mean, I think already you kind of have hit upon that.
If I could add one caveat to that, and this is just because I am a scientist and I want to be perfectly accurate. Every cancer is quite different. And so some of those hallmarks appear in certain ones, some appear in other ones. For example, blood cancer, of course, is not going to have structural changes, but, well, you know what I mean.
Yeah, absolutely. So, and I guess I should clarify as well. So the work that I've done in this area was looking at autofluorescence for
colon cancer?
Yeah.
So I'm familiar with the study.
Right. You cited one of my papers. I was very excited. So I'm coming at it from a very narrow view, and you kind of clarify in your paper. You do a really great job of this, actually. I shouldn't say kind of. That you're looking at these specifically for the selected targets, right? And esophageal and then ovarian. Which are endothelial cancers. So you can definitely get into a pretty small domain here, but that's important because you want to be specific about what you're looking for. Okay. So I'll go ahead and mention it because it'll probably happen more, but the camera is kind of being funny, so there might be frequent pauses and restarts. So I apologize. But one thing that I remember from colon cancer was even when you get kind of larger lesions at the surface, so not that it's particularly fun to look at, but when you're looking at colon cancers visually at the surface, that you might not see it. It doesn't. Some of them, they look like, oh yeah, that's something. I need to take a careful look. But a lot of them don't. They might be mildly discolored if you're looking at it in the visual spectrum. There's nothing particular about the surface that really stands out. So you really cover this, that the techniques you're looking at, they're looking kind of below the surface or at spectrums. So,
yeah, and so the depth, the concept of under the tissue depth is definitely important. And so some cancers, it's not a problem. Others, it's a massive problem. Even within a cancer, there are many different subtypes. And so some of the work I do is in gastric cancer as well, very similar to esophagus, and that you still use the same endoscope. But there are there are multiple subtypes. One has big, well-defined tumors, not that hard to see. One is completely diffuse and subsurface, and it's almost impossible to see. And so that's a case where you really need something depth resolved.
Yeah. Okay, well, great. We've set the stage. Everybody knows that cancer is bad, but particularly in this specific domain for your dissertation, you were looking at esophageal, ovarian cancer. The earlier you can detect them, the better. They're both endothelial types. They both have similar characteristics, and you've clarified why for these specific cancers they have unique biomarkers, and we want to look at them in specific ways. So you chose in your dissertation to focus on OCT, multiphoton imaging, and then fluorescence. You used, I think, MFM. I want to say is the acronym. I don't remember what it fully stands for.
MMP, I think.
Okay, maybe, yeah.
Yeah.
So why don't, before we delve into how you actually applied them and tested them, let's just kind of set the groundwork for how they operate and what are they, I guess, what are they good for and what are their limitations? We can go ahead and start with OCT, which was really exciting. I've heard about it before, and you did this really great description of kind of how it's like a Michelson interferometer and how it operates with Raleigh and Mee scattering. I never know how to pronounce it. So I'll let you describe it.
Yeah, sure. So I think OCT is an awesome technology, and it is used clinically in some fields now. So ophthalmology, they have OCT devices to measure retina and the thickness. I think I alluded to it earlier, but essentially OCT, as you said, is an interferometer, and it's just trying to interfere the reference arm with whatever light comes back from your sample. Usually you scan point by point, and kind of the secret sauce with OCT is that if you have a relatively broad spectrum, meaning it's not a laser, but kind of a 100 nanometer bandwidth source, if you take that spectrum, disperse it, so you get like if you take that light, you disperse it to get a spectrum, and then take the Fourier transform of that, it actually gives you the depth profile of the interference, not just one single point in space. And so that makes it really nice to get 3D data, because you can just do a 2D scan and you get a 3D volume. Advantages of that are that, again, it's great for microstructure. Any difference in refractive index produces a Fresnel reflection. You have Mee and Rayleigh scattering from cells, nuclei, stuff like that. What it's not very good at, essentially it's non-specific, that you're going to get scattering off of whatever cell there is. Doesn't matter if it's a cancer cell, doesn't matter if it's a healthy cell. So you do have to kind of look at the larger picture. A lot of it is qualitative. A lot of my work was focused on quantification of these images. But
which I really liked. We'll get into how you did that.
Sure. Yeah, definitely. But yeah, I think it's important because I think that ultimately you do want to have some kind of nice benchmark or threshold that says, okay, this is a dangerous point, and below that, maybe not, above that, maybe so. But OCT is good for all those sorts of things. It's also pretty robust to things like, working distance. Like, yes, you have to be some working distance away, but it's not super duper sensitive to it.
And so there's a trade-off with OCT, which you mentioned in your dissertation. There's three kind of key things that you highlighted. You care about lateral resolution. That makes sense.
Yep.
Am I trying to look at something extremely small or maybe a slightly larger microstructure or millimeter size structure? The delta Z, so the axial resolution that you can resolve, and then the depth of penetration. And so I think you mentioned kind of the trade-off on wavelength and how that plays in. So do you mind just kind of discussing that a little bit? Sure,
yeah. So the lateral resolution is similar to any lateral resolution concept in optics. It's probably going to be dictated by diffraction, but depending on how your system is, might be aberration limited. OCT systems tend to be really low numerical aperture, and so they don't suffer from terrible third-order aberrations. A lot of it ends up just being Gaussian beam math and that type of thing. The wavelength, however, that actually, the bandwidth of the wavelength defines the axial resolution, so it doesn't really matter at all what your optics are, but however broad your spectrum is, it's going to limit your depth resolution. The wavelength is really important for penetration depth, and so if you're working with fresh tissue or living tissue, you're going to have a couple of absorbers that really limit the window in which you can work. One of them is blood, as we talked about. You get some nice, a little bit of nice space in the near infrared that lets you penetrate pretty deep before water takes over. And then water absorbs things above a certain wavelength. I don't exactly remember what it is, but so with OCT, that operates somewhere on the order of 1,000 to 1,500. That also is nice because you don't have quite as much scattering, so you can, again, penetrate more deeply. And because we know that scattering is proportional to 1 over lambda, or 1 over lambda to the fourth. And so OCT has a nice kind of a Goldilocks zone around that, 1,000 to 1,500. And so that's typically where you'll see people working with that.
Okay. I would really recommend people read your dissertation as well, because you do a nice explanation, not only of kind of the background and math behind the OCT, but for my domain, what I work in now is metrology of mirrors, right? So static things, and we're doing a lot of interferometry and trying to get down to, the nanometer, sub-nanometer in some cases. And you do this great description of kind of contrasting that with this bandwidth of your source and why that plays into OCT. So it's really interesting, and I recommend people read that portion. So the next one, I mean, we can choose whichever one you want, but why don't we do the multi-photon?
Sure. So what's good is both the fluorescence and multiphoton is the same process. And so in both cases, you're illuminating with photons, they get absorbed, promote electrons to higher energy states, those eventually decay, and then emit fluorescent light. The difference between standard fluorescence and multiphoton is that with multiphoton, you have two photons, so to speak, of a higher wavelength getting absorbed at the same time, approximately. And so you could have two 1,000 nanometer photons get absorbed and then produce the same fluorescence as a 500 nanometer photon.
Yeah.
And so the reason we like that, again, is the penetration depth thing, that if you use infrared light, it penetrates more deeply. And so you can access just nice, kind of depth profiles, a couple hundred microns at least below the surface. For multiphoton, that's more of a label-free technique in terms of what I was doing. And so that's looking at those natural, like, metabolic markers or... That is the main one, metabolic, but I am interested in some other ones. Like there's certain ones that are indicative of senescence in cells, which is when they kind of go into a dormant state. But in my dissertation work, I think it was mostly looking at the metabolic factors. Yeah. The other thing with multiphoton is that while you have the fluorescence, we call that two-photon fluorescence, and you can do it with 3 and theoretically 4 and more, but it gets harder and harder. You also get what's called second harmonic generation. And so this isn't really a fluorescent event because you don't have any energy loss, but you have a perfect conversion from as perfect as it gets, from 2 photons to 1 photon, and it's more of a scattering process. But what's nice is that it's very strongly produced by collagen in the body, which is the connective tissue, there are other connective tissues, but it is one of the main ones, holds everything together. And so you get these beautiful maps of collagen tendrils and fibers, and it makes for a really excellent visualization of when that extracellular matrix gets disrupted by cancer. Yeah. And so with multiphoton, you get that for free, essentially, if you have the right filtering on the back end. Whereas with standard fluorescence, you'll only get the fluorescence.
Okay. And you kind of implied it right there, but cancerous tissue, the extracellular matrix, including collagen, gets heavily disrupted. That was something we looked at in the autofluorescence. There's no downside, is what I've heard so far. So are there any limitations, I suppose, to multiphoton?
I think in the broader sense, definitely. In that, yes, it can penetrate somewhat deep into the tissue, but nowhere near as deep as like ultrasound. Okay. Or any radiological imaging modality like X-ray. And so that's always going to be an issue with optical modalities, is maybe 0.5 millimeter. OCT can go a bit further, maybe 1 millimeter of good data. But that's just a broad limitation of all of these.
What's the field of view? How does that compare to OCT, I guess, because we haven't gotten to fluorescence just yet?
Sure. Yeah. For multiphoton, you typically are working with small fields of view. So maybe max would be like 0.5 millimeter by 0.5 millimeter. You can, with like lab-based systems, you can take multiple fields of view and stitch them together into big images. But usually the lateral resolution on a multiphoton will be like 1 micron. And so when you're scanning a beam over a certain area, you'll have to consider things like the scanning speed, aberrations on the edge of the field, and so on. But usually it ends up being, maybe plus or minus 200 microns by...
Yeah, so a pretty small area.
It's a pretty small area. So that is another limitation, is that you can only look at one small area. Yeah. You can't cover a massive space.
Right. And so that brings us to the last one, which I want to say was multispectral fluorescence.
Yes, because we worked with... So this was contrast agent based in this work. And so in this case, what you're trying to do is you find some biomarker. It could be a cell surface receptor. It could be a certain biochemical that gets kind of spread out among the cells. And what you do is you try and conjugate a fluorophore, so something that lights up really well, with some kind of antibody targeted to that biomarker. And so we looked at 2. One was these things called MMPs, that stands for matrix metalloproteinases. And this is actually what degrades the extracellular matrix. And so when the cancer wants to start metastasizing, it puts off these MMPs. It kind of gets rid of the barrier that prevents them from getting to the blood vessels to get elsewhere. And so that we thought was a good marker. And so that just had I don't remember what color fluorophore it was, but it was probably green or something like that. And then the other one we looked at was folate. So folate is biochemical. I can't remember its role in the body, but it's very relevant for the reproductive system. And so we wanted to look at that for the ovarian cancer specifically because I believe the amount of folate goes down when you have cancer. And so the idea here was we bound that to some antibody. You would apply that to your patient. Usually it's done through an IV, could be topical. And then in this case, you could do a wide field of view. And so this could kind of be an approach where you do a, large area screening. You might see an area light up with this fluorescence, and then you go in with OCT or multi-photon to get a really high resolution kind of confirmation.
Okay, well, perfect. So OCT, multi-photon, multispectral fluorescence. It makes sense to me. They all sound like really great modalities. They're kind of looking below the surface, and you're going to get structural information. You're going to get fluorescent information. So I guess I have a dumb question, so to speak. Why do we not use them now, right? Why are doctors, and I think that this is an important question, actually. They are used, I know, in labs. Why are clinics not using? Why are clinicians not saying, here's my OCT and my multi-photon, imager and my fluorescence imager. Here you go. I can see anything, right?
Yeah, great question. So the barriers to translation are variable, and I think it depends context to context. In some cases, it is that the technology is not mature enough yet. I think that's probably the case with multi-photon, is that the idea of implementing some kind of clinical handheld multi-photon device, it's not quite there yet. I think multi-photon systems tend to be big, bulky, expensive. You can't wheel it around in a little cart. Yeah. We are getting there. I think some people have made some really amazing kind of miniaturized systems, but it's not quite there yet. I think that's also a case where things like working distance it's pretty sensitive to that, and so it's a little bit harder to control. OCT, on the other hand, has seen amazing progress in getting into the clinic, and so in cases like ophthalmic optics, they have them in the clinic. Specifically to look at retinal thickness. I use the word they generally, but people have tried to translate an esophageal OCT endoscope. I'm not exactly sure why that one didn't really work out. The company was called 9 Point Medical, but it looked like a great device. It provided beautiful images. I think in that case, it was the perhaps just a little bit too different from the standard of care. Yeah. And so to get something adopted, you need buy-in from the physicians and stuff. So it may have just been wasn't quite ready. They weren't quite ready yet.
Right.
In terms of fluorescence, that is used fairly frequently for things like fluorescence-guided surgery. The limit there is the contrast agents that get clinically approved. And so any of those have to go through the FDA. There are some general ones, like some just light up blood vessels. It's called ICG, works pretty well. But things like MMP, folate conjugated fluorophores, you would have to go through extensive clinical trials for that. And I think some groups are doing that, but it just takes a long time to get one of those approved by the FDA. And you also have to have data to show that the sensitivity and specificity is good enough that it's worth using. And
I'm gonna provide my own opinion here, and I kind of inferred this as well from your dissertation, but if I'm wrong, please correct me. But I think part of it is, we covered this in a biomed class when I was an undergrad, that clinicians have a lot of info coming at them. And we kind of liken this to a pilot in a plane, right? They've got all these screens and buttons and things beeping at them, and you just kind of get information overload. Okay, well, this is, I don't know, this is beeping, this is flashing red, and this is yellow, and I don't, it's too much. It's too much, right? And even if it's not necessarily giving this warning sign, which actually can be helpful, it's going to be qualitative. I'm gonna look at something. Well, maybe it looks funny. Maybe I'll look at it more. And so I think that it's a big ask for clinicians to say, okay, well, we've got 3 extra things we want to add. Maybe we can get them in one endoscope, but maybe we can't. So this is kind of a comical description. I'm being hyperbolic here, but imagine telling a doctor who already is overworked, here's 3 new endoscopes, there's 3 new computer screens, you figure it out. It's too much. And so I bring this up because your work does this really great, your dissertation does this really great job of how do you synthesize this all into kind of a single thing that the clinician can care about. And I presume this is your ongoing work. So, first of all, do you have any comment on that?
Sure.
Is it accurate or?
Yeah, I'd say it's extremely accurate. I think in my experience, which is limited, you'll have different groups of clinicians. Some of them are really into technology, and they're the ones who are your advocates. Mm-hmm. And it's like, those are the people you want to work with. Then there's going to be the ones who probably will never want to adopt something new. That's fine. But then you have the middle ground, and that's probably the people that you just described in terms of they're so overwhelmed right now that they're probably not going to be jumping to do new things. But I think that if, for example, there was a lot of support from the community and like a lot of data showing that it's better than existing methods. And then even if it gets integrated into their training, it's like that eventually could be impactful. So I'd say absolutely, but you want to make it as easy as possible for them to use a new thing.
Yeah, right. So how did you do this? You kind of described there's these three key factors. There's segmentation, feature detection, and then model building and categorization. I want to say, so can you just kind of describe what those are and how this plays into taking this disparate data and getting something that's all uniform?
Absolutely. So I think what you described is pretty common among image analysis pipelines in general. And the concept of segmentation, that's essentially removing unwanted parts of your image. That is relevant for things that are like OCT, where you might do a larger area. For example, we were imaging a bunch of ovaries. In this case, it was mice, so they were pretty small. And we wanted to have some kind of analytical pipeline that automatically gave us relevant numbers, and we didn't want it contaminated by the background. And so segmentation was removing that mm-hmm. background information from the actual tissue. Something like multi-photon, we didn't need to segment because it had a small enough field of view that everything was relevant. Feature extraction, again, this is a pretty general image analysis topic, but the idea there is you just want to come up with quantitative descriptors of things that you see in the image.
Yeah.
It could be anywhere from, like, if you have a network of lines like collagen, things like how straight they are, how dense they are, that type of thing. Something we looked into for OCT is essentially called the texture of the image. And so it's kind of the local variation in brightness. And mm-hmm. so if you have a bunch of cells packed together, it's going to be really bright for a while because it's like really high contrast. Mm-hmm. But then if you have like voids, which you do have in ovaries, they're essentially where the eggs grow, mm-hmm. You're going to have a dip and go back. And so we were trying to quantify that to give us these numbers that represented what our eyes are actually seeing. Mm-hmm. And so that's feature extraction. There are so many methods for doing it that could be its own dissertation, basically. Yeah. We looked at texture because it's pretty well used in biomedical images. I think people are pretty comfortable with it. They know what it represents. We did use the same thing for multi-photon. We looked at some kind of frequency-based features, and so you do things like Fourier transform for those collagen images since they're so kind of line-based. And then for standard fluorescence with contrast agents, in that case, you just take the average brightness. Yeah, that one's easy.
How right? That makes sense.
And then those give you a bunch of features, and what do you do with them? Well, you try and build some kind of mathematical model to achieve a goal. In our case, we wanted to do classification. Was it cancer? Was it normal? Pretty much the most basic task you can think of, binary classification, yes or no. And again, same with feature extraction. There are dozens upon dozens of different classification models. I think we limited ourselves to a pretty well-known one called mm-hmm. linear discriminant analysis. I think it's usually used in cases where you have quite a few features and not tons of samples. So almost all of biomedical imaging.
Yeah, right.
I think things like, MRI, X-ray, you can get many, many, many samples and start doing cool machine learning stuff. But for these initial scenarios, you want to do a nice, well-constrained model. But the goal there was really to get it to purely based on the numbers, tell you what is the probability that it's going to be cancer or normal, and classify it into one of the two groups.
Mm-hmm. And so you completed your dissertation on ex vivo study of rats, that you kind of had these two comparative models. So how did it turn out? How did it work?
Yeah, so it worked pretty well. Definitely well enough to motivate continued research. It certainly wasn't a 100% accurate model. And I think if it was, I'd be suspicious. I think there's so much heterogeneity in the body that it just doesn't seem feasible to really ever have something that's perfectly predictive. Mm-hmm. I want to say the accuracy, and you can say it in terms of sensitivity, which is, how much false positives are there, the specificity, which is how many false negatives are there, etc., or just pure accuracy, what percent were correctly classified. I want to say it was somewhere on the order of 80 to 90%, which was pretty good. There are caveats to this, which is that, of course, this is an animal model. This is not perfectly recapitulating human, but you got to do those studies to really motivate doing this work on human patients, and to go through all the risk and reward for that.
Yeah, and headache, I would say.
Yeah,
to be totally frank, right? I don't know if you can say that, but I definitely have this memory that kind of getting an IRB approved study on humans approved is a lot of work. So, and you need a lot of evidence for. No, trust me, it's really worth doing this. So
absolutely, especially when you're putting a device into a person. It's I think it's great if you can leverage existing technology. So like esophageal, a lot of our devices are meant just to fit in the working channel of an existing endoscope, and that makes this much easier because you're not really putting anything new into the body. You're just putting it into something that's going into the body. Right. So yeah, it's amazing. That big headache, I think.
Yeah, we had a. I'm very sympathetic to it, but, when we had human testing, you had to ask the person before they were going to go into the emergency room, not emergency room, pardon me, but into surgery. Hey, are you okay with us, studying you? Mm-hmm. Nobody really wants to hear that, right? And some people were extremely kind and generous and said, yeah, of course, no problem. But it's just to say... biomedical studies have this uphill extra obstacle, I'd say, as compared to other domains of optics anyways.
No, absolutely. And I think, it's good that they have that step in the procedure because everyone needs to give informed consent.
Sure, of course, yeah.
But even with receiving ex vivo tissue samples, where that's essentially stuff that they're already going to be having, like we get lots of samples from the hospital, just from routine procedures where they're already having tissue removed.
Right.
A lot of people aren't comfortable with it. And a lot of them have good reason, given that some groups have been really, marginalized in terms of being used for medical experimentation without their consent and stuff. But I think it is good that we have those processes. But I think that also goes to speaking about having good collaborators and people who work with the patients, because when it's presented as an option to them, there are many different ways in which you can present that, and I can say that some of them have a much higher success rate.
Yes, absolutely. I think that's fair, and it would probably fill up a podcast episode of its own of those various ways. So you did the ex vivo study. You also produced a prototype endoscope that synthesized these three modalities. And I don't mean to diminish this or jump ahead, because this is really, in my opinion, a colossal amount of work, and it was really good work and really well documented. But for the sake of time, where did that leave you? Right? You completed your dissertation. You're now a professor. Is your lab studying the same thing? Was there follow-on work to that? I know there was. You mentioned it in the dissertation. So what was that follow-on work, and how's it progressing, I suppose?
Definitely. Great question. So yes, certainly I continue to work on these topics. I would say that from the consideration of the concept of research independence, my PhD advisor still has kind of been leading the ovarian cancer work. And then I kind of needed to branch off and spread my wings and fly.
Right.
I really have stuck with a lot of the GI cancer, though. So esophageal, gastric. We have prototype endoscopes that we're hoping to do some in-patient studies, at least in the next year or two. It just takes a long time. Certainly, that prototype that I built in my dissertation, it needed significant iteration. I think the first iteration or prototype worked okay. I think it was not a bad first go, but certainly with any engineering challenge, you find all sorts of issues with your first attempt and need to improve on that. So thankfully, I have a team of amazing students now who are leading the charge on that. But yeah, so right now we are still focused on esophageal cancer. I broadened a little bit to gastric cancer since it's also a big issue, basically the same characteristics, also accessed using the same type of endoscope. And then we're also looking at other applications of the technology too. Mm-hmm. So things like surgical guidance, where it's like you already know that the tumor's there, you're going in to take it out, but you don't necessarily know how much to take out, where are the boundaries, you certainly don't want to leave any more, any of it in there.
Right.
So we're also looking at other applications too, and where optics can really help improve the healthcare system.
Mm-hmm. And I guess I kind of glossed over this, and I definitely should not have, but biomedical optics are really hard to make. They're really small. You're fitting this, I think I might have this wrong, but I want to say that in your prototype it fit into, or commonly they fit into like a 3.2 millimeter diameter endoscope, and you're combining 3 modalities. You're fitting a lot of stuff in here, and so it's not only not a trivial optical design, engineering, and manufacturing task, it's a really hard one. So anyways, I just wanted to kind of give proper credit where credit's due. But
thank you. I think what's interesting is that the challenge to me is a little bit different than, let's say, like astronomical optics. Because astronomical optics, you're going to be trying to maximize the resolution, sensitivity. In biomedical optics, I think it really is this idea of like cramming as much as you can into a tiny little space and trying to get as much information as quickly as possible. So you might not need the best resolution possible. You might be okay with, maybe, let's say the diffraction limited resolution is 5 microns. Maybe you're okay with 10.
Yeah.
But it's like those other things tend to be the real headaches that require 90% of the work.
Yeah. Well, if you have time, it's 5:40. I know that we've kind of pushed past time, but if you have time, I wouldn't mind asking you maybe 10 minutes of not optics necessarily related questions.
No, I'd love to.
Okay, great. So the first one, this is actually loosely optics related, but what do you think's next for biomedical imaging? What's in your opinion, what's kind of the most exciting technology up and coming?
I think that is an excellent question. I personally think it is the continued development of things like machine learning and how that can help complement the field. I don't think it's the solution to everything. I think anyone who really reads into it realizes that it's going to be really good for certain things, not so good for other things. But I think it can help lower some of the barriers that we see in terms of you collect a bunch of data, what do you do with it? And a doctor might not have time to go through every frame in a video with 3 different modalities. And so having these really advanced mathematical models, whether it's machine learning, AI, whatever, I think will be really exciting to see how that can complement the field. And it's used in a lot of different ways, not just like image classification. And so I think that'll be exciting. I think something that's kind of interesting is, the title of my dissertation was Multimodal Imaging. The concept of multimodal, adding different types of imaging, it kind of comes in and out of favor depending on the time of the decade, we could say. Mm-hmm. And I think we'll probably converge on some consensus or something in the next 10 or 15 years, which is that sometimes it's helpful to use more than one, sometimes it's not.
Yeah.
And really coming up with a standardized way in which you can kind of figure out what is the best approach might be really helpful going forward too, because I think right now we're still trying to figure out how to approach that.
Yeah, I certainly agree. I'll step back slightly on your machine learning point. Again, just going back to this analogy or portrayal, even if it's made up, that imagine a clinician, you have all these screens and signals coming at you. I do think that that's a domain where machine learning can contribute and say, I can kind of cut down the fire hose of info coming to you to only the relevant info.
Absolutely.
And do some kind of discernment on that. So I entirely lied. I said I'd be off of optics and biomed. I'm going to keep asking those questions, but why should students go into optics, and why should they specifically go into biomedical optics, in your opinion?
Yeah, and I'm extremely biased given that I've studied optics since I don't know, 19 or 18. I think that optics is broadly a really exciting field because it has a role in almost all science and technology today, including things like consumer electronics. I know a lot of my friends went to work for Apple, Google, Snapchat. It's it's all over the place now, in addition to various fields of science like astronomy and obviously biomedical, and even things like plant sciences. It's like they use optics almost every day for measuring things like spectra. Mm-hmm. And so I think a degree in optics is really kind of a license to go and make a contribution wherever you feel like you want to.
Yeah.
You can find I think, valuable contributions in any field. I think biomedical optics would be a great fit for anyone who's interested in learning a little bit more beyond optics. And so, like, yes, you have to know a lot of optics, you have to know imaging, all that stuff, but you do have to understand things about the body, about biology, cellular processes, physiology, that type of thing. And I think that, to me, that's quite rewarding, because I honestly, when I started digging in, I felt like I was back as a freshman in college, even though I was in grad school at some point, and it was like fundamentally fascinating to learn about the different processes of how the body works, how our cells turn just raw material into energy. It's absolutely fascinating. So I feel like it's a really fun field, because you get exposed to a massive variety of science, not just limited to one field, which limiting to one field is totally fine too. Yeah, but I do really like it's kind of refreshing getting to learn all this new stuff.
I think that you'll know it if you're motivated by biology, biomed, whatever, umbrella you want to call it. I think that another thing that can be common is it's really rewarding, because you're tangibly contributing to helping people.
Absolutely.
And that's not to say that other domains don't, but it's very tangible, right? There's such a direct, at least in my brain, it was so clear of, well, I'm doing this and I can see how that will help people.
Yeah, you can go meet the people that you might actually. Yeah. Whereas I think other fields, that might be 100 years from now.
Yeah.
And I think that's just as valuable. Like, you need to have the whole spectrum. But I agree that if you want to feel like you're making an impact on people's lives in the immediate sense, I think biomedical is a great fit for that.
Yeah. I'll add it actually before we go on, but the one other thing to say is that I think if you find biology easy, mm-hmm. biomed can be a really rewarding path to follow. And the reason that I say that is I've spoken to a lot of people who found it hard, particularly in optics, right? Particularly in optics, you get a lot of people who are very physics, math oriented, and for whatever reason, the nature of biology just doesn't particularly click well. At least has been my experience. And I had the exact opposite experience. For me, biology, oh man, this is, for whatever reason, the narrative around it and how we kind of explore it and think about it really clicked, and math and physics didn't. And so I, of course, decided to not do the thing I was good at, but that's my own decision.
I think it shows you have the grit.
It shows something, I don't know. So how would you recommend someone, but particularly a graduate student, prepare for a career postgraduate in academia or in industry?
Great question. I think I'll assume it's an earlier stage grad student, so they have time to do longer term things. If you want to go into academia, I think it has a strong emphasis on publishing, and so get as many publications as you can. I think journal papers are great. Conference papers are fine. You need to be comfortable speaking, comfortable communicating your work. And then you have to get some familiarity with teaching and make sure you actually like teaching. So if you want to become a tenure track professor who does teaching, you're probably not going to enjoy your job if you hate teaching, because it is a big part of the job. It takes up a lot of time. I personally love it. It's my favorite part of the job. But just be aware that is a main component. There are other careers in academia that are pure research, and that I think might be more along other people's alley. If they really don't like to teach and they just want to do research, that's totally fine too. But just do a little bit of research on what each path might be composed of, because I think there's a common misconception that I think a lot of people think that the job distribution is more research than teaching, but during the semester, I would say it's about equal. And if you don't like half your job, then that's not a good place to be.
Yeah.
I think for industry, get as many hands-on skills as you possibly can. And so that includes things like programming, working with hardware, even things like mechanics, electronics. All of these things are going to serve you extremely well, because you'll have you might have a specialty and let's say you're an awesome optical designer, but having some awareness of how that's going to integrate with the rest of the system is going to be extremely important, so that you can make the best contributions to that project that you can. So I think that would be my recommendation, is that in academia, yes, you'll still want to do good lab work and stuff, but emphasize the publishing, presenting. If you can do some teaching, even if it's a TA. I love TAing as I was a grad student. Whereas with industry, I think you still need to communicate what you do, but it doesn't have to be as formally documented as like a publication. But really those hands-on skills are what people are going to be looking for.
Mm-hmm. I always really appreciated Dr. Koschel. I think he's still the associate dean, I assume. He told me near kind of the close to when I was graduating, he said, well, you know, the point for you, if you're going to industry, is not that you know, my topic happened to be deflectometry, not that you know deflectometry better than anyone. The company's probably not going to hire you for that. It's that you know how to solve problems. And I thought that was really insightful. And I liked it a lot.
He's a smart man.
Yeah, right. That's true. He's a funny man.
He is funny.
So, did you? This is a little bit oddball question. Did you enjoy talking about your research when you were a graduate student? And how does that compare to now? You know, your lab's work. Do you enjoy talking about that now?
Yeah, I think that I enjoyed talking about nuances a lot more as a graduate student because I think that's what I was working with every day, you know, is that you're doing these little things in your bigger project, but you're drilling in a lot. Whereas these days, I feel like I get the 10,000 foot view a lot more frequently. And so I'm not speaking very well right now. I am much more excited about talking about the bigger picture and more of the longer term things. I think because now I kind of see it like that. I think that also you increase your comfort level as you do it more and more. And I've certainly had lots of opportunities now to talk to people about it, get excited about it. And I think it makes it even more fun when you're more like comfortable with what you're talking about.
Yes.
Whereas I think I questioned I still do. I mean, it's like the more you know you don't know. But then once you get comfortable with what you don't know, I feel like that's the true power.
Mm-hmm. I like that a lot. I don't know. I don't know that I want to put you on the spot, but I can say for myself in grad school, certainly kind of starting out, it was not fun, and then it was really not fun, and quite a bit of imposter syndrome. And I think by the time that I left, I thought, yeah, I feel a lot better about this. You know, I feel a lot more confident. I was pretty unhappy at one point, but by the end, I really liked it. And it's taken some years in industry to recognize, looking backwards, I still had a lot of imposter syndrome. So, you know, feel free to comment on that if you want or not. But
no, I think that imposter syndrome, if you don't have it, then I would question your sanity as a human. I think that to me, it is just a sign of humility a little bit, in that people should be aware that they don't know everything. And I think that a lot of times that becomes kind of amplified in the sense that you think you don't know anything. And that's kind of where imposter syndrome comes up. I honestly still feel that way sometimes. And so certainly it is not something that is, a unique experience. I think it's great to talk about it if you can with your colleagues, because probably everybody feels that way a little bit. But I think as you go forward, I agree that in grad school, I feel like for me, the first year wasn't bad. But then I think years 2, 3, it got harder. And I think it was, you dive deeper into a topic, and then you really realize what you don't know.
Yeah.
And then by the end of it, you start to like pick back up, and then you're again more comfortable with where you stand, and you gain confidence that you can learn what you need to. Mm-hmm. So you don't need to know everything, but you should be confident that you can learn what you have to.
It's amazing. One of my coworkers, he was telling me some parenting advice, which I had asked him, and he said that one of the things that he and his wife do for their children is that anytime since they were born that their children said, well, I don't know that. I don't know how to do it. They would always say, yet. You don't know yet. And that's an astonishing thing to learn at, how old am I? However old I was, let's say 33. It's an astonishing thing to hear that and have it click that much. But man, it resonates, and you don't get that, or I didn't get that during grad school, as much, where I had these moments and you say, well, that person over there really knows it. They really know, E&M or geometrical optics or whatever the case may be. And I don't. And that's bad. Well, you don't know it yet, and you're pretty smart. You can figure it out, and you eventually will learn it. And I don't know, maybe that's easier said than done. So
yeah, well, I think it also speaks to people recognizing their strengths. Is that everyone's going to come from a different background, and whether that means that you, I don't know, did chess club throughout all the high school, or if you played sports, it's like those are going to give you different strengths as you go forward, and learning what your strengths are and how to leverage them to best serve you in your career, I think is really critical. And that is kind of a concept in addition to that concept of like you can learn and achieve whatever you want that I try and integrate into some of my undergraduate teaching as well, because I feel like learning it early is the best time to learn it, because then you can go about your life with agency and know that you can achieve something, and it's just a matter of effort. And it's great if you have people to lead you and help you along the way. But, if you're at the point where you're studying a hard topic in college, it's like you've got what it takes.
Yeah. Okay. These are the last ones. I promise. I'm sorry. I'm taking up a lot of your time. But truly, these are now off optics, off biomedical. Last book that you read and recommended to someone.
I read a lot of books. I don't know. I'm trying to think what I recommended to someone. So, yeah, I am a big fan of sci-fi and fantasy. And I think that the last book that really grabbed me to the point where I'm like, I couldn't put it down and I'd recommend it to someone was, it was a series by Joe Abercrombie called the First Law series. It's a bit like Grimdark in terms of the context. So if you're not into Grimdark, then don't read it. But excellent characterization. I feel like reading about it. I think that series is mostly about the characters, not necessarily as much about the plot, but absolutely terrific and very interesting. And there's quite a few of them now. I want to say there's 2 trilogies plus like 4 in between books that I haven't read all the in between ones yet, but I've done the 2 trilogies. And yeah,
I always, whenever I look at a new sci-fi or fantasy series, I always try to make sure that the author is near or has finished them. There's a book that I'm reading for the 4th time or something by Patrick Rothfuss called The Name of the Wind, and he still hasn't published the 3rd book. And at this point, it's getting a bit egregious. But anyways, I digress.
You don't want it to go the way of Game of Thrones.
Right. But I try to keep positive. I don't want to say anything harsh to someone I don't know. So,
no, I feel you.
So the last book that you did not finish. On that note, what's the last book that you said this is not worth finishing?
So I was reading a book about the history of the Civil War, and it was not a bad book by any means, but it was a very, very dense book and a very, very long book. And so I admit that I don't remember what the name of it was, honestly, but my brother is a huge American history buff, and so he has all sorts of books on that type of stuff. But yes, I did not finish that one.
Yeah.
I thought it was a great book, just a little bit too much.
The best advice that you've received.
Best advice that I've received. I think that probably, when I was a student, I had a lot of like anxiety issues, especially like social anxiety, and it was really tough for me to like go to any kind of, social gathering. And I think that someone just asked me that it was my like undergraduate research mentor, and I feel like I was pretty close with him because I worked for him for almost 4 years. And he just asked me like, "What are you afraid of?" And not in a mean way, in a nice way, because I was kind of like remarking on it to him, and it just made me kind of think about like, why is this so hard? And that didn't necessarily make it super easy, but it really gave me the push to be like, I need to take this into my own hands and do something about it. And I feel like after kind of pushing through, I realized how fun it was to go to social stuff, and I love it now. So it's, I feel like that was just a very helpful piece of advice where it's like, it wasn't even really a piece of advice, but it just made me think. And it made me think like, oh wait, I can do something about this. And so, yeah.
I like that a lot. What's the worst advice you've ever received?
I think someone once told me not to rely on anyone. I think that I feel like that's kind of crap advice. I feel like I get where it comes from if people have been hurt by others, but I feel like if you surround yourself by good people and people you can trust, then you should rely on them, and you'll make it much further than if you're just on your own.
I heard that you have traveled quite a bit. I like traveling. So what's your travel advice? What should I know for my next big trip? My next big international trip. Let me say that.
It might depend a little bit on where you're going. I think that what I would recommend is reading forums online about people who have recently visited. Because, like, if you Google something, you're going to come to some article that somebody wrote and you have know nothing about them. They're probably just trying to get clicks to get advertisements, and it's not very helpful. If you go read, like, forums that aren't necessarily, that popular, you can get some really interesting recommendations on things to do, things to be aware of in terms of customs, how to interact with locals and that sort of thing. I found that very helpful, especially in countries that I'm less familiar with. Mm-hmm. Like I'm pretty comfortable in Europe. I feel like I understand European culture, but more recently I've been visiting Korea, Japan, stuff like that, and it was just really helpful to kind of get advice both from locals who go to those forums and say, no, this is how you do it, and people who just went. So that would be my 2 cents.
Okay. And my last question, I promise, thank you very much for your time. What country have you not been to, but you really want to visit?
If you asked me a year ago, I would have said Japan. Mm-hmm. I always had a dream to climb Mount Fuji. And so that was I had a trip planned and then COVID happened. And so
my wife and I had the same thing. We had a trip planned to go to Japan, not necessarily to climb Mount Fuji. And it didn't happen. We still haven't been. So it's high. It is about as high as it can be on our list.
Yeah. Well, I highly recommend. So a country I still really want to visit. I would like to visit many countries. I think the question is which one most. I think New Zealand would be pretty high up there. I'm a big fan of nature. Love hiking, camping, backpacking, and also a huge fan of Lord of the Rings, and that was filmed in New Zealand. So I'd say that one.
If you don't mind unsolicited advice from me, the Milford Sound, there's a trek through the Milford Sound. It is without a doubt the best hike I've ever experienced anywhere on Earth. Wow. And it distinctly captures these transitions between different biomes and different, just things feel different. And it feels very Lord of the Rings like.
Nice. So Milford Sound. I'll keep that in mind.
I just cannot recommend it highly enough. You can do kind of a guided thing so people carry your stuff and or you can do your own. I don't know, it's really slick, and New Zealanders are incredibly delightful people. So
that's awesome. Well, thank you for the suggestion. I'll definitely keep it in mind.
Sure. Okay. Do you have any last things that you want to say or ask?
I think just thanks again for the opportunity. It's been an absolute pleasure to talk to you, Logan.
Great. Well, thank you so much, Travis.